name of subject, internal combustion engines, name of chapter, introduction, name of the topic, Otto cycle. Contents: the Otto cycle and its basics. Dear friends, in the last few lectures, we already started to see the first chapter, or we can say the introduction chapter of internal combustion engines. We started with the definition of engine, then we had the different components and constructional details of engine. In the last lecture, we discussed about the engine terminology or the nomenclature. Also, we discussed about the different classifications of the internal combustion engines. Now, we are moving towards to understand the very important term or the very important thing about the engine, the cycles. Engines are always working on two basic theoretical cycles, and these cycles are mainly called as a Otto cycle and another one is a diesel cycle. Now in this lecture we are going to concentrate only on Otto cycle thoroughly along with the different derivation or the mathematical equations for the Otto cycles. Okay. Unless and until understanding of this particular Otto cycle, we can't move to proceed to understand the working of 4-stroke engine or the 2-stroke engine itself. Okay, so we just concentrating on this particular Otto cycle in this lecture, and in the next lecture we will concentrate on the diesel cycle. We'll understand it. Okay, so here we have Otto cycles PV diagram. PV diagram is nothing but pressure versus volume diagram. Okay, so in this case on the y-axis here we have a pressure line, and on the x-axis we have the volume line. I think all of you are having the knowledge of thermodynamics. Here the knowledge of thermodynamics playing a vital role to understand this particular concept. Okay, so this particular diagram indicates the point of pressure and the point of volume during the cycle of operations. Okay, and this cycle is invented by Mr. Nicholas August Otto. That's why on his name this cycle is called as the Otto cycle. All the working of petrol engines or SI engines are depending on this Otto cycle. This is one of the basic theoretical cycle for the working of all the petrol engines or spark ignition engine. Okay. So one by one we will understand. Now we are directed to notes. With the help of the notes we are going to understand this Otto cycle in detail. Yes. So here is the note, Otto cycle, and this is basically for SI engines. This cycle is also called as a constant volume cycle. Why it is called as a constant volume cycle? Later on we will discuss on this also. So this cycle was invented by Mr. Nicholas Otto in the year of 1876. That's why this cycle is called as a Otto cycle itself. And this is the basis of today's all petrol engine or SI engine. So again the pressure versus volume diagram, and another diagram, this is TS diagram. This TS for temperature versus this particular entropy, TS diagram we have on our screen itself. So one by one we'll understand these processes. So as I told you earlier, here you required the basic knowledge of the thermodynamics, then we can understand these things thoroughly. So with the help of this pressure volume diagram, what we can understand, here I am explaining. Okay, so let us consider, suppose before going to understand this particular PV diagram, here what is the use of this PV and TS diagram? We must have to understand. That is the logic. What is the logic behind it? Okay, so whenever the petrol engine will work, that time this PV diagram shows the pressure point and the volume point at the different processes which may happen inside the working of engine or during the working of engine. And similarly this TS diagram shows the temperature as well as the entropy during the working of the engine itself. Okay, so let us consider, suppose here is one engine. Okay, So let us consider this is a theoretical diagram or the block diagram of the engine, and this is the piston. So this is the piston and this is the connecting rod. Okay, so as we already discussed or already had about the constructional or terminology diagram, this is V suffix C, this is the clearance volume, means this is the top dead center position of the piston, this dotted line, and this dotted line is the bottom dead center position of the piston, means the piston is always reciprocates in between this particular space. This is called the swept volume, as we know. Okay, Vs, which is represents over here, and this particular space above the piston surface, above the top dead center, this is called a clearance volume. Swept volume, clearance volume, and this is again the total volume of the cylinder. So here I am just showing this engine in horizontal direction to understand this particular PV diagram. Okay, so in this case, what are the different processes for the Otto cycle? Here we understand. So let us consider process 0 to 1 is a suction process. Okay, 0 to 1, process 0 to 1 is a suction process. Process 1 to 2 is a compression process. Then process 2 to 3, this process 2 to 3 is heat addition process. Then process 3 to 4, this process 3 to 4 is isentropic expansion process, and finally the 4 to 1 and 1 to 0, this 4 to 1 is heat rejection and 1 to 0 is again exhaust process. These are the different processes which were invented by Mr. Sir Nicholas Otto in the year of 1876. Okay, and this is the basis of today's all SI engine or petrol engine. Okay, so these cycles are very typical cycle and need to be understood before going to understand the working principle of the petrol engine. That's why this is essential one. Okay, so as we just discussed, 0 to 1 is a suction, 1 to 2 is isentropic compression process. So as I told you earlier, you need to have a knowledge of thermodynamics to understand these particular cycles. 0 to 1 is a suction, 1 to 2 is isentropic compression, 2 to 3 is the heat addition, 3 to 4 that is isentropic expansion process, 4 to 1 heat rejection process, and 1 to 0 is nothing but called the exhaust process. Okay, now what happened during these cycles? Here we are going to understand. Okay, as we know, this is the cylinder. Suppose let us consider this external surface, or this particular portion is a portion of a cylinder, and where the piston will reciprocates up and down from in between BDC to TDC, TDC to BDC, like that. Okay, now in this case, initially what happened? Initially, during suction, that is process 0 to 1, piston will move from top dead center to bottom dead center. Please concentrate on this particular mouse indicator. Piston during suction stroke or suction process, piston will move from top dead center. Let us consider this is the top dead center and this is the bottom dead center. Piston will move from TDC to BDC, and this process or this stroke means what? Piston will travel always in between TDC to BDC or BDC to TDC. Once it reaches from TDC to BDC, it completes one stroke. Another stroke from BDC to TDC, like that. That is nothing but called as the stroke itself. So during this process, during suction, when the piston is traveling or moving from this TDC to BDC, it completes the one stroke, and this stroke is called as the suction process or suction stroke. And this PV diagram indicates what? During suction, the pressure during the cycle remain constant. Which pressure? Whose pressure? The pressure of air and fuel mixture, because air and fuel mixture is the basic fluid which will come inside the engine cylinder, and this keep remain constant, which indicates with the help of the process 0 to 1, and volume is going to increase. My dear friends, as the air and fuel mixture will come inside the engine cylinder, as piston will move from top dead center to bottom dead center, its volume is ultimately going to increases, but its pressure remain constant. Again, during the second process, again piston will move from bottom dead center to top dead center. During this process, indicates with the help of the curve 1 to 2, and this is the isentropic compression process. Whatever air fuel mixture will come inside the engine cylinder, that will be going to compress, and that process is nothing but called as a compression process. Now we can understand with the help of this PV diagram, during process 1 to 2, the volume is going to decreases. Now if you concentrate here, during process 0 to 1, its volume is going to increases, but during process 1 to 2, it revert back, or we can say it will going to decreases, but pressure is going to increases from P1 to P2. Are you getting? Okay, so this is the second process. Now during process 2 to 3, what happened? Q suffix S is nothing but called as a heat addition take place. How heat addition takes place? Now 0 to 1 is a suction, 1 to 2 is a compression. Now at the end of compression, at the point 2, there is one more device, as we already discussed in the last few lectures. That device is nothing but called as a spark plug. What is the role of spark plug? Spark plug will provide some amount of spark inside that compressed air and fuel mixture, and that burning will start to take place during the spark plug provides the spark, and this indicate process 2 to 3. This is called heat addition process, which represents with the help of letter Q suffix S. This process QS, this is the heat supplied or heat addition takes place by the spark provided by the spark plug, and during this process volume remain constant. If you concentrate over here, volume remain constant, but pressure will going to increases from P2 to P3. This is again very important one. Pressure will going to increases tremendously. Now again piston will move from TDC to BDC after spark plug provides the spark. Then expansion process will start to take place. Whatever amount of air and fuel mixture will burn, that will started to convert it into the gaseous form, and because of that gases, again its pressure, gaseous pressure, piston will move down from P3 to P4, from TDC to BDC. This process is called isentropic expansion process. See, 0 to 1 suction, 1 to 2 is a compression, 2 to 3 is a heat addition because of spark plug provides the spark, 3 to 4 is isentropic expansion process. Again piston will move to BDC, and finally again piston is moving from BDC to TDC. Heat rejection takes place, and 1 to 0 is exhaust, means that exhaust gases will come out from the engine cylinder. So this is about the Otto cycle. This cycle completely called as a Otto cycle. 0 to 1 suction, 1 to 2 compression, 2 to 3 heat addition, 3 to 4 expansion, 4 to 1 rejection, and 1 to 0 is the exhaust process. And during this process, with the help of this diagram, we can understand what about the value of volume and pressure during the cycle of operation. And similarly, with the help of this particular TR diagram, we come to know what about the temperature condition and this entropy condition during the working of the engine. Okay, initially 0 to 1, this compression, 1 to 2, 0 to 1 is a suction, 1 to 2 compression, 2 to 3 heat addition, then this particular 3 to 4, this is the expansion process, 4 to 1 heat rejection, and 1 to 0 is a exhaust process. Okay, means during this process, what about the temperature, T1, T2, what about the entropy, this S1, S4, like that. With the help of this diagram, we can get different temperature points and the entropy point during the working. Okay, so dear friend, this is called the Otto cycle itself. So when we are going to define the Otto cycle on mathematical basis, in the term of derivation, we have to write the equations. Okay, so how we can write the equation? Here we can understand this Q suffix S is nothing but called as the heat supplied. As I told you earlier, this QS is heat supplied by the spark plug. Spark plug provides the spark, means there is an addition of heat. That's why we can say QS is nothing but heat supplied. Now how we can write the equation? Heat supplied is nothing but this mass of fuel into calorific value M into CV into T3 minus T2. Now what amount of heat is supplied over here? Maximum pressure is what? This P3. Minimum pressure here is P2. Similarly, in terms of temperature, what is this heat addition process? 2 to 3. T3 minus T2. That is, in this case, this T3 minus T2 is a maximum temperature, and this is the minimum temperature during the heat addition. That's why we can write the equation mass of fuel into calorific value into that temperature difference T3 minus T2. This way we can calculate heat supplied. Always remember, dear friends, mass into calorific value we will get a heat supplied multiplied by the temperature difference. So this is the equation of QS, and similarly we have to write the equation of Q suffix R. This is nothing but Q suffix R is heat rejected. Now here is again T4 minus T1. Only there is a need to change this equation. Whole equation is same, MCV into T4 minus T1. So here we got the equation of QS and QR. So generally, whenever we are going to calculate the efficiency, how we can calculate the efficiency? Efficiency is nothing but output by input. So in this case, what is the output and what will be the input? So in this case, whenever we are going to calculate the efficiency is nothing but output means what? In terms of work done of the cycle. Okay, whatever work done is being by this particular cycle is nothing but called as the output, and here we can write work done divided by input. Input means what? Whatever heat we are going to supply during the cycle is nothing but called as the input. So in this case, what is the work done? Whatever amount of heat we are going to supply minus whatever amount of heat is going to rejected, means this QS minus QR divided by total heat supplied. What total heat supplied in this case? So in this case, the heat supplied is Q suffix S. So that we can write QS minus QR, that is heat supplied minus heat rejected, that is nothing but work done divided by input heat supplied. So simplify the equation, we will get the equation of efficiency 1 minus Q R divided by Q suffix S, and again further simplification of the equation, here we have efficiency is equal to 1 minus this QR. We already calculated the value of QR. This is MCV T4 minus T1, and here MCV T3 minus T2. Put these two values in this equation of QR and QS, and finally MCV will get cancelled. The remaining equation will be efficiency of Otto cycle is equal to 1 minus T4 minus T1 divided by T3 minus T2. Give equation number 1. This is in the form of temperature. Now again, after further simplification, further simplification, we will see. Now we know that here we are assuming the compression ratio is nothing but small r. Letter small r represent for compression ratio, and this is equal to V1 by V2. Again, move to the diagram. This V1 by V2 is represents the compression ratio. See, process 0 to 1 is a suction, 1 to 2 is a compression. So the compression ratio is V1 by V2, and similarly for the expansion ratio, this is process of compression and this is process of expansion. Now the compression ratio is V1 by V2 and expansion ratio is V4 by V3 from the diagram itself. So we can write over here, let us consider compression ratio is R, represents V1 by V2. This is the compression ratio, and similarly expansion ratio is equal to V4 by V3. So dear friends, you just understand whatever amount of air and fuel mixture will get compressed, that amount only will get expand. Is it right? Whatever amount of please concentrate on my statement. Whatever amount of air and fuel mixture will get compressed during the process of compression, that amount only of air and fuel mixture will get expanded. Okay, so we can equate these two equations. Compression ratio is equal to expansion ratio, so that we can write both these equations are nothing but small letter r. We can write. Okay, so here we got V1 by V2 is equal to V4 by V3 is equal to r, small r. We consider. So similarly, we know the ideal gas equation. Ideal gas equation is equal to PV is equal to mRT. Characteristics gas equation we know. As I told you earlier, here we required the basic knowledge of thermodynamics. That is very essential and important. Okay, so PV is equal to mRT. Suppose m is unit mass. That's why I am taken here 1 as it is. Assume it. So PV is equal to RT. So when we are going to apply this particular PV is equal to RT equation for this process 1 and process 2, then how we can write the simplified equation? P1 V1, take this T over here, P1 V1 divided by T1, and for process 2 P2 V2 divided by T2. Which are those processes? For compression and expansion. So we are assuming two processes are there. Okay, so P1 V1 by T1 is equal to P2 V2 by T2, and similarly we know PV raised to gamma is equal to C, and this is the process of adiabatic. Okay, and this gamma is nothing but called as the adiabatic index. So similarly, if the number of processes are there, we can write P1 V1 raised to gamma is equal to P2 V2 raised to gamma is equal to P3 V3 raised to gamma, like that, and so on. Okay, so here we are just taking up to two equations. P1 V1 by T1 is equal to P2 V2 by T2 from this equation, simplified one, and from this equation we have P1 V1 raised to gamma is equal to P2 V2 raised to gamma. So after further simplifications, again take this T2 over here. So T2 by T1 is equal to P1 by V1 to the denominator of this P2 V2. So we can write P2 V2 divided by P1 V1. So again in this case also, now separate out the terms of P2 by P1. Take the P1 over here, and this V1 by V2, and the gamma is common. That's why we can write V1 by V2 raised to gamma. Okay, so simultaneously we are doing the simplifications of this particular two terms. Okay, so again simplified this equation now. T2 by T1 is equal to, now here we have the value of P2 by P1 is equal to V1 by V2 raised to gamma, so that, dear friends, we can put the value of P2 by P1 in this equation. So replace P2 by P1 with this V1 by V2 raised to gamma and rewrite the equation. We will get V1 by V2 raised to gamma is equal to into V2 by V1. Okay, so if you concentrate, here is V1 by V2 and here is V2 by V1. So we have to match the both terms. Okay, we have to get the both terms equally. So we can write this V1 by V2, V1 by V2, that time the power will be minus 1. That's why finally we can write V1 by V2 raised to gamma minus 1. This is the simplified equation. Okay, now similarly, if T2 by T1 is equal to V1 by V2 raised to gamma minus 1, again see this particular diagram. T2 by T1, this T2 by T1 is equal to V1 by V2 raised to gamma minus 1. So can I write for T3 by T4? Yes, definitely we can. Similarly, we can write for T3 by T4, and finally we can write T3 by T4 is equal to V4 by V3 raised to gamma minus 1. Baga. See, V4 by V3 raised to gamma minus 1. So with the help of this diagram, we can here write this T2 by T1 is equal to V1 by V2 raised to gamma minus 1, and similarly for T3 by T4 is equal to V4 by V3 raised to gamma minus 1. Again after further simplification, T2 is equal to, take this T1 over here, T1 into this V1 by V2 raised to gamma minus 1, or we can just equate the term T2 by T1 is equal to V1 by V2 means what? Yes. Now again see this term, V1 by V2 is nothing but R, that is compression ratio, and V4 by V3 is a again that is exponential ratio. Here we just considered, we understood. Okay, so put that values over here. V4 by V3 is replaced by R, and similarly this V1 by V2 is replaced by R, and V4 by V3 is replaced by R, so that we can write this T2 is equal to T1 into R raised to gamma minus 1, and this T3 is equal to T4 into R raised to gamma minus 1. So again, see equation 1. Here we got already equation number 1, so we can replace the values in this equation. We got the values of this one, T4, T3, etc, etc. So put that values, or T1 and T2 values, etc, etc. So put that values. So 1 minus T4 minus T1. So we don't have the values of T4 minus T4 and T1. So we have the values of T2 and T3. So again, I'm showing you equation number 1. Where is that T3 and T2? Yes, to the denominator. So we have to put that calculated values in equation number 1, replace that values, and we got T4 minus T1 divided by T4 into R raised to gamma minus 1 minus T1 into R raised to gamma minus 1. So after further simplification, we can write the T4 minus T1 1 minus T4 minus T1 divided by this R raised to gamma minus 1 is a common term in this equation, and we can write into T4 minus T1. So again, further simplification, this T4 minus T1 and this T4 minus T1 will get cancelled. What is remaining? 1 minus 1 divided by R raised to gamma minus 1 is nothing but called as the final equation of Otto cycle efficiency. We can say the mechanical efficiency of Otto cycle is equal to 1 minus 1 by R raised to gamma minus 1. So this derivation is very important. This will ask to you for 6 to 8 marks. Explain Otto cycle in detail along with its mechanical efficiency derivation. Okay, hope you understood this derivation in well manner. You have to do some practice to understand this. Okay, here I just explained each and every term for your understanding purpose. Okay. So similarly, when we talk about the another formula, mean effective pressure equation of Otto cycle, so the equation is, or the formula is, this is indicated with the help of letter P suffix M, or simply you can write MEP, mean effective pressure for Otto cycle. Its formula is area of PV diagram divided by length of the diagram. Area of PV diagram is that PV, pressure and volume diagrams area, divided by whole length of the diagram, and this is the formula. This mean effective pressure for Otto cycle is equal to P1 into R in bracket R suffix P minus 1, another bracket complete, and in another bracket R raised to gamma minus 1 minus 1 bracket complete. Whole equation is divided by this particular gamma minus 1 into R minus 1, where this R suffix P is nothing but called the pressure ratio. So this is all about for the Otto cycle. So today we discussed thoroughly the Otto cycle in details along with its derivation of mechanical efficiency and mean effective pressure. So thank you so much, dear friends, for watching our today's session. Thanks a lot. Thank you.